So before we start talking about the boost converter, are you hearing any echo?
No, sir.
Okay. So we'll try to do one or two maths just at the beginning of each and every class. So I will start with a very simple example that is given in your hard book. So this is very simple example of 6.1. So it says, suppose you have a DC to DC buck converter that has the following properties. So let me first draw the DC to DC buck converter. So this is my DC to DC buck converter. I have already started the recording, so you don't need to record that. Jahid Sadiq.
Yes, sir. Thank you.
So suppose we have a simple DC to DC buck converter like this. This is my output voltage V naught. This is my input voltage Vs, and this Vs value is given as 50 volt. So your input voltage is 50 volt, and then your duty cycle is given as 0.4. So duty cycle is a ratio. So as you can see, it will be a dimensionless quantity, and then your L value is given as 400 microhenry, and your capacitor value is given as 100 microfarad. Okay. So now this resistance value R value is given as 20 ohm. And the operating frequency, that is your Fs, which is 1 over Ts, is given as 20 kilohertz, which is 20 multiplied by 10 to the power 3 hertz. Now, they said, assume all the components are ideal, meaning your switch is ideal, your diode is ideal, your inductor and capacitor, all of them are ideal one. So first thing they are asking is that what should be the output voltage? So the output voltage V naught, in the last class we saw that it should be D multiplied by Vs, right? So 0.4 multiplied by 50, it should be how much?
20.
So it should be 20 volt, right? Now they are asking about the maximum and minimum inductor current. So in the last class, we discussed about IL max, which was your V naught. Then it was 1 over R plus 1 minus D multiplied by 2LF. So if you put this value, your output voltage is 20. Then 1 over R. So your resistance value is 20 ohms plus 1 minus D. So 1 minus 0.4 divided by 2 multiplied by your L value is 400 multiplied by 10 to the power minus 6, and your frequency is 20 multiplied by 10 to the power 3. So what should be your IL max? Can you calculate this value? Can anyone tell me the value?
1.75.
1.75 amps. Okay. So now if I want to get the IL mean, it will have the same equation. Instead of plus, it will have the minus value, right? So it should be 1 over R minus 1 minus D divided by 2LF. So 20 multiplied by 1 over 20 minus 1 minus 1 minus 0.4 divided by 2 into 400 into 10 to the power minus 6 multiplied by 20 into 10 to the power 3. This value should be
0.25.
what?
0.25.
0.25 amps, right?
Yes, sir.
Now, they are asking about the ripple voltage, output voltage ripple. So what was the output voltage ripple equation? So the output voltage ripple which was my del V naught. What is the equation for del V naught? In the last class, we derived the condition, right? So this should be the del V naught. It should be 1 over 8. So my del V naught is 1 over 8 multiplied by 1 minus D into V naught over LC Fs whole square. So if I put this value 1 over 8, 1 minus D value is 0.4, then your L value is 400 multiplied by 10 to the power minus 6 multiplied by C value is 100 multiplied by 10 to the power minus 6, and your frequency value is 20 multiplied by 10 to the power 3. So what should be this value?
So 0.47.
0.47 volt, right? So what should be the percentage of ripple? So if you
So
try to
0.47%.
So nominator V not missing is equation.
So what is the del V value? Oh, okay. So you haven't put that this V naught, right? So your V naught is nothing but 20 volt. So what should be this value?
স্যার ফ্রিকোয়েন্সি টি স্কয়ার হবে না স্যার ফ্রিকোয়েন্সির মান
Right. This should be square. So what should be this value?
So 0.0937.
7 volt. So if I try to get the percentage of ripple,
Sir, V naught is 50 volt
what?
in the nominator. In the numerator, V naught, you have write 20.
Your output voltage is what? 20 volt, right?
Okay, sir, sorry. Yes.
So percentage of ripple, it should be 0.0937 divided by your output voltage, which is 20 multiplied by 100. That should give you the percentage. So what should be the percentage?
So 0.4685.
0.4685%, right? So these are the very straightforward example to calculate or design the DC to DC buck converter. So now everything in the buck converter, actually, we are considering it to be an ideal case. But the ripple that will appear across the load, actually, it will come from the capacitor. So if you consider a realistic capacitor, this capacitor, instead of having a purely DC capacitor, actually it should have some resistor associated with it, right? So what is happening here? So instead of C, it should have a resistance that is known as resistance in the capacitor. So if you want to see the total voltage change del V, so due to the current change del IC, actually what is happening here, your total change del V, it will be very approximately equals to del V, it will be very approximately equals to whatever change is happening del IC multiplied by RC. Because the capacitor voltage drop, it will be in practical cases very small as compared to what is being dropped across the resistance. So you have to remember this, whenever there is a ripple at the output of the load, this resistance is the key influencer for this one. Okay. So now what I will try to do, I want to try one example again, which is 6.2 and 6.3. It will be the similar one. You do it by yourself. So that should be your homework. Okay. And if you face any problem understanding this, then you can ask me in the next class. I will try to sort out that portion. Okay. So let me draw the buck converter again. So suppose, okay, somebody raised their hand. Can you tell me the question you have?
Sir, in the diagram, did we consider RC as internal resistance of the capacitor?
Right, not the external one. So
Okay.
whatever ripple you will find across the diode, across the capacitor, this resistance will be contributing to that one.
This delta V is voltage drop.
Yeah, so that
Okay,
should be this delta V, actually, it should be the summation of these two drop, right? So it should be, so if I say it a phasor form, so this delta V should be equals to del VC, that is the drop happening due to this capacitance, and then it should be del V R. But actually what is happening, this thing, the drop across the capacitor, because it has a large value. So as the capacitance has a large value, what is happening to her? So whenever you have a large value, so these reactance become very low, right?
Ji sir.
So whatever value is being dropped across the total capacitor circuit, this voltage drop will be the key contributor to that one. You got my point, right? Any question?
আর স্যার আমরা যদি ক্যাপাসিটর একটা কনসিডার করি সেটার মধ্যে তো ইন্টারনাল রেজিস্ট্যান্সটা কনসিডার করছি, সেটার সাথে আমরা আবার এক্সটার্নালি ভিআর কেন?
We are not considering external VR. So suppose the total voltage across it, it's del V
ওকে ওকে ওকে
phasor. So this should be my del VC, right? And the voltage
Yes.
drop here, it should be del
ডেল ভিআর
VRC, right?
yes.
So I should write it as del VRC, right?
Yes sir, this makes more sense.
So this del VRC is nothing but the current change multiplied by the resistance, right?
Yes sir. Okay sir, I understood.
Okay. So in your example 2, what is happening here? They said design a buck converter to produce an output voltage of 18 volt across a 10 ohm load resistance. So let me draw the buck converter first. So suppose this is my buck converter. I have an ideal diode here. Then I have inductance L, and then I have capacitor, and then I have load. Suppose this is my plus minus V naught, and this value is given as 18 volt. And the resistance value given here is 10 ohm. And they said design for the continuous inductor current, and it says the output voltage ripple must not exceed 0.5%. So percentage of del V naught over V naught, it should be not more than 0.5%. So what should be your del V? What should be your del V naught?
0.5 into 18.
So it
into
should be 0.05 multiplied by the output voltage, right?
Yes.
So what should be the value?
0.9. Okay.
How much?
So 0.09.
0.09 volt.
Sir, only
No,
0.9.
0.9.
0.005. Sir, if
0.5, oh,
0.5%.
sorry, yes, it should be 0.005, right? Because 0.5%, if you divide it by 100, it should give you 00, right? After point. So what should be the value?
0.09.
Okay, so your value should be 0.09 volt. So now it is said the DC supply voltage is 48 volt. So your Vs is nothing but 48 volt. And then they said design for continuous current Then it says specify duty cycle. Then it says the switching frequency. The values of inductor and capacitor. The peak voltage rating, of each device and the RMS current in the inductor and capacitor. So now, if I want to see the duty cycle, what should be my duty cycle?
Sir, output voltage divided by the source voltage.
So that is very easy, right? Output over input, or it should be Vs. So your output is 18 volt. Your input is 48 volt. So what should be your duty cycle?
0.375.
Okay, 0.3375. So that should be your duty cycle. So yesterday we were talking about the value of inductor current that can have effect of changing your inductance value, right? So we saw that if you decrease the inductance value, this current will shift downwards, right? And then we'll finally have a inductor value for which we'll have the extreme point of the continuous current, right? For which we got I mean, IL mean, it equals to 0. And then from that one, we got the L mean value, right? So what was the L mean value? In the last class, we derived the equation for L mean value. So what was the L mean value? Can anybody remember? This was the L mean value, right?
Yes, sir.
So L mean is nothing but 1 over twice R Fs multiplied by 1 minus D. So now we know the D value, we know the R value, but we don't know the switching frequency, right? So we have to choose a frequency for which the loss will be very low, because if your switching frequency is high, what will happen? This switch will be turned on and off too often. So there will be a switching loss across the switch, right? And if you put the switching frequency very low, then what we need to do, you have to put a huge inductor in the circuit. So we have to make a trade-off between the switching frequency and the inductor size. So are you getting what I am trying to say?
Can you please explain it again?
Yeah, so what is happening here? Suppose, as I said, if you put too much switching frequency, here at that transistor T1. So what will happen? This transistor will turn off and or too fast, and as you turned it on and off too much time, there will be a switching loss across the device, and this switching loss is dependent on the frequency. But if you put this frequency very low, this switching loss will be less, but in order to have a continuous current there, the minimum inductance required meant will be high, right?
Yes, sir.
So we had to make a trade-off between the inductance value and the switching frequency. So in your book, actually what is they did, they choose a switching frequency of 40 kilohertz. And based on that, the 40 kilohertz switching frequency, they designed the buck boost converter. Sorry, buck converter. So if I consider this switching frequency to be 40 kilohertz, then what would be my L min value? So it should be 1 over twice multiplied by 10 ohm multiplied by 40 kilohertz. So 40 into 10 to the power 3 multiplied by 1 minus 0.375. That gives you L min value.
Sir, I think there was a slight mistake in the derivation of the L-min equation.
What was that?
Sir, the resistance value should be in the numerator.
All right, yeah. So in that class, this is minus. So if we put it there, this R will get it at the top, right? So it should be here.
Yes, sir.
Okay, sorry, I did that mistake. So if you put R at the top, so your R should be here, right? So this, okay, let me correct that. So your R value should be at the top, and then R should be here. So R should not be here. So 2 multiplied by 40 into 10 to the power 3. So what should be this value? What should be this value?
78.
78.125.
78.125
125.
farad. Sorry, Henry or micro Henry?
Micro Henry.
Okay, micro Henry. So this is the minimum of the minimum inductance that you should put in the circuit to have the waveform like this, when your I mean would be 0, right? So this is the critical situation. But should we put the inductance value like this, or should we choose the inductance value higher than that, so that we have the inductor current in the continuous mode like this? Should
Sir,
we
we
have
should
the
choose
critical
slightly
value,
higher.
or so this L min will provide this waveform, right? So if you put the value, L value more than L min, so what will happen? This waveform will shift upwards, right?
Yes, sir.
So in your book, what they did, they, in order to design the circuit, they took the value L in the circuit. It is 25% higher than the L mean value, which is 1.25 multiplied by 78.125 microhenry. That gives you, what should be the value?
So 97.5.
97.5 microhenry. Did you understand why we take 25% more than the mean value?
Sir, can you take any value other than 25%?
Yes, you can. You can. You can take 10%. You can take 25%, 50%. The more you get the higher value of L, the more you have the freedom, like this. Okay, so the more you put L value, as you put more and more L value, the current will shift upwards. Okay.
Yes, sir.
So there is no thumb rule like you have to take 25%. You can take 10%, 15% based on your choice. Okay. So now we got the values of inductor. Now we choose the switching frequency based on the trade-off between the inductance and the switching frequency. Now we need to know the capacitor value. So how can we calculate the capacitor value? My capacitor value, how can we calculate the capacitor value? By using this equation, right? Or this equation. So your C value is nothing but 1/8 multiplied by 1 minus D over del V naught over V naught multiplied by L into Fs whole square. This is the value we got in the last class, right? So if we take this in the denominator, it will be del V naught over V naught, right? So what should be your capacitor value? It should be 1 minus 0.375 divided by this. In percentage, we got 0.5%. So in actual value, it should be 0.005, right? Multiplied by your L value is 97.5 into 10 to the power minus 6 multiplied by your switching frequency that we considered here is 40 kilohertz. So 40 into 10 to the power 3, that gives you what is your this value?
Sir, 100.
How much?
100, sir.
100 microfarad, right? So now, we got the inductor and capacitor value. Now we need to know the peak voltage rating of each device.
স্যার এফএস এর স্কোয়ার হবে না?
Right. But it should give you 100 microfarad, right?
স্যার এল মিনিমামের সাথে .125 গুণ করলাম কেন? 1.25.
Right, because we said L minimum, if you choose L minimum, your current should be like this, right? The extreme point of the continuous mode, right? But if you chose L value more than in L minimum, then what will happen? The more you put L value, this current, instead of having this current, it will be shifted upwards like this. Okay, so that will be more continuous current, more stable continuous current than the extreme point. If you choose L value less than L min, so what will happen? In the last class we said our inductor current will be like this. It will charge, it will discharge, goes to 0 and stays 0 for some time. Again it will charge, discharge, goes to 0 for some time. So in order to make sure that your circuit is having a continuous current, because it says design the circuit for the continuous current, we have to choose a L value such that this L value must be greater than your L min value. You got my point, right? But as I said, it should not be always 25% more of that. In your book, it has chosen this value to be 25% more than the minimum value. You can choose any value. It might be more than 10% or 20% or 30%. And based on that L value, you have to choose the value of C so that the current operates in the continuous mode. You got my point? Do you got my point?
Yes, sir.
So now it says the peak voltage rating of each device and the RMS current in the inductor and the capacitor. So what should be the current rating of this transistor? In the last class, we said what should be the current rating of this transistor?
IL max.
Yeah, that should be the current rating, right? But what should be the voltage rating of the inductor? Sorry, this transistor. So whenever this transistor
Vs.
will get open, so the entire Vs, it will appear across this, right?
Sir.
Is that clear to you all?
Yes, sir.
In the last class also we said that in mode 2, what is happening here? So actually this circuit would look like this. So in mode 2, you will have this transistor that will be open and this diode, it will be short circuited, right? So this diode, it will be short circuited like this, and then you will have inductor and then capacitor, and then you will have the load, right? So if this diode is short circuited, all the voltage that is your input voltage, this will appear across the transistor, right?
Yes, sir.
So what should be the voltage rating of the transistor?
So 48 volts.
So the voltage rating of the transistor should be 48 volt, right? Now, when the transistor is operating, so when the transistor is operating, what will happen to the diode? This diode should be operating in open circuit, right? Right? When this
Yes, sir.
transistor is operating or short circuited, then the entire Vs will appear across the diode, right? Making this diode operating in reverse bias, right?
Yes, sir.
So the maximum reverse bias voltage that the diode should handle, it should be also the
Yes.
source voltage, right? So the peak inverse voltage of diode should be what? 48 volt also, right?
Yes, sir.
Now, see, when your transistor is operating, what should be the voltage across the inductor? It should be Vs minus V naught, right?
Yes, sir.
So if it is Vs minus V naught, so when T is on, when T1 is on, then the voltage VL, it should be Vs minus V naught, right? What is your Vs?
48 volt.
volt, right? And what is your V naught? 18 volt. So 48 minus 18, it should be 30 volt, right? And when the inductor is, that transistor T1 is not operating, what should be the voltage across the inductor? It should be minus V naught, right?
Yes, sir.
So when T1 is off, then VL should be minus V naught, which should be minus what? 18 volt, right? Right?
Yes, sir.
So what should be the maximum voltage that the inductor should withstand?
So 30 volts.
30 volt.
30 volts. So the rating of the inductor should be 30 volt. Is there any confusion about that?
No, sir. Sir, can you explain it again, sir?
Yeah, so what is happening here? When my T1 is on, what is happening? This T1 gets on and this diode gets open, and this is my inductor, and here it is my capacitor, which is connected to the load R. This is my plus minus V naught. So the inductor voltage here, VL, it should be what? This point is connected to Vs, this point is connected to V naught. So the inductor voltage here, it should be Vs minus V naught, right? Right?
Yes, sir.
Yes, sir.
But what is happening when your T1 is off, but your diode gets closed, then what should be the value of VL? This plus terminal is connected to the ground and the negative terminal is connected to the positive terminal of V naught. So your VL value would be minus V naught, right? So we have to check what is the maximum value of VL that would appear across the inductor during these two modes. And by comparing this value, we got that this should be the highest voltage in terms of magnitude, not by the polarity, right?
Yes, sir.
Any question? Any question?
স্যার T1টা যদি মানে ক্লোজড না থাকে তাহলে ভিএসটা কিভাবে ওইটার অ্যাক্রসে কনসিডার করা হয় এটা একটু যদি বলতেন।
If V1 is not, T1 is not closed.
ইয়েস স্যার,
You
মানে
just
স্যার
take
এই ফিগারে
a you just
যেখানে
take a Kirchhoff's voltage law. So minus Vs, then you have this voltage plus VT1, and this is short plus 0. It should give you 0, right?
yes sir,
So
yes
your
sir.
VT1, it should be equals to Vs, right?
Okay sir, thank you sir.
Now your capacitor, it is always connected to the load, right? And this output voltage, we are always keeping at 18 volt. So what should be the capacitor value? Capacitor rating?
18 volts.
Capacitor should have rating of 18 volt. So this is our voltage rating. Okay. So how about the current rating? So in order to determine the current rating, so okay, before I go there, so did you talk to Dr. Ashik sir? What did he say?
Yes, sir, the class has been delayed for 15 minutes.
Okay, thank you so much. So now, as you know, the inductor current here, inductor current will be like this, right? So it will be jumping and going down, again jumping and going down, and it should have a average value, right? IL average, and that should be equals to my I naught. We discussed that in the previous class, right?
Yes,
Yes,
sir.
sir.
Yes, sir.
So your IL average, or we can simply say IL, that should be equals to your I naught, which is nothing but V naught over R. So your V naught is 18 volt and your resistance is, what's the resistance? 10 ohm, sorry. So 10 ohm. So what should be your this value? 1.8 amps, right?
Yes, sir.
And this distance between IL max and IL min, this distance is my del IL, right?
Yes,
Right?
sir.
Yes, sir.
So that was my IL max. And this point was my IL min, right? So del IL during the charging period, what was that? It was Vs minus V naught over L multiplied by D into Ts, right? So what is my Vs value? Vs value is 48 minus 18 divided by L. What we choose for L? 78.125. So 78.125 into 10 to the power minus 6 multiplied by D. D is 0.375 multiplied by TS, which is 1 over Fs. So 1 over Fs we considered is 40 kilohertz. So 40 into 10 to
Sir,
the power minus 3, 10 to the power 3, right? Yes.
so shouldn't the L value be 97.5? That 78.125 is L minimum.
Oh, sorry. Yes, it should be 97.5. Thank you. Thank you. Yeah. So we designed the circuit for 78 point. So yeah, I am doing something very hurriedly. So that's why I'm making some mistakes here. So 97.5. So what should be my del L?
Sir, 2.88 ampere.
2.88 amps, right? So last class we discussed about if this is my IL, we talked about my IC, it will be the replica of the IL current. Apart from that, what is happening there? Whenever this current is below the average value, it will start from like this, right? So it will be like this. So this thing, the difference between top and bottom of the IC current, it should be also equals to my del IL, right?
Yes, sir.
So now what should be the IL max? IL max, it should be IL plus del IL over 2. So IL is 1.8 plus del IL is 2.88 over 2. So that should give you
Sir, 3.32 ampere.
3.32. 3.32.
Yes, sir.
32 amps. Okay. In your book, it is 1.24, 3.24. So did you do any
If
mistake?
No, sir. If you have taken all the values um after decimal of the digit 2.88, then you would have gotten 3.24.
Yeah, so 2.88, if you make half, it would be 1.44, right? And if you add it with 1.8, it should give you 3.24, right?
Yes, sir. It is 3.24.
Okay. So this is the maximum current that the inductor has to deal, right? And minimum current, it will be less than that one. So the current rating of the inductor, so the current rating for the inductor, it will have two component. One is the DC component, and another is the triangular waveform, that is the component. So if you know the equation, something like that, IRMS is actually all the components that you have, IRMS 1 square plus IRMS 2 square dot 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 all the frequency component that you have. Did you ever see this equation?
Yes, sir.
So now, then you have a simple DC waveform. This DC value is 1.8 amps. And then you have a triangle. So the maximum value of the triangle here, it should be del IL over 2, right?
Yes, sir.
So if this is your triangle and this is your height, so the RMS value of a triangular wave is what? Suppose you have a triangle like this. You have a triangle like this. And then this is your maximum current. That is I max. So the RMS value of this triangular current, IRMS, it should be the actual magnitude Im divided by √3. You can derive it, or if you have any problem deriving this one, I can help you with that. Okay. So now, what should be this triangular length? It should be del IL over 2, which is 1.44, right? Del IL over 2 is 1.44, right? That should be the height of this triangular wave. So what should be the RMS value of the triangular waveform? IRMS, I can say triangular, it should be 1.44 divided by √3. What should be this value?
Sir, 0.831.
0.831 amps. Now, then this triangle or the inductor current has two components. One is the DC component and one is the triangular component. So the actual RMS current of the inductor, it would be using this equation, we can say IDC square plus IRMS delta square, right? Because we have two components in the inductor current, right? Right? Because
Yes, sir.
we had this current component and also this component. So we had only two components. So what is your DC value? 1.8 whole square plus this thing is 0.831 whole square. So what should be the RMS value of the inductor?
So 1.98.
1.98 amps. So this is the RMS rating of the inductor. So the RMS current rating of the inductor should be 1.98 amps. So this should be all the components designed for the buck converter. Is there any question regarding this? Any question?
No, sir.
So should I go to the next topic?
Yes, sir.
So now today we'll start discussing about the boost converter. How much time we have?
Around 20 minutes.
How much?
20 minutes.
Okay. So the boost converter, in the buck converter, what is happening here? If you remember, we put the inductor close to the load. Now what happens if we choose to put the inductor to the source side, or you can say we will be shifting these things towards the source, and we will be putting this source to, it will be connected, the source will be connected to the inductor, and this load with the capacitor will be connected after a switch. So what I am trying to say is that for the DC to DC buck converter, what is happening here? Suppose we have a DC source, then we have a switch here, then again we have another switch here, then we have an inductor, then we have a capacitor, and then we have a load. This is my plus minus V naught, right? And this is my source voltage. So what we will try to do here is that we will keep these things and we'll switch this thing in such a way that we'll put this source next to the inductor. So let me draw this. Suppose you have a inductor, then this side it is connected to the source. Okay, then you have a switch here, and then you have another switch here, and then we put the load and with the capacitor. Do you understand what I did?
Yes, sir.
So why we are doing that? Because in the buck converter is, we say that your output voltage V naught is D multiplied by Vs. So whatever is your voltage, your output voltage is less than that one. So what we are going to do, if we switch the ends between the source and the output load with the capacitor, then let's see what happens, whether their characteristic is reversed or not. So with that concept, suppose now we are just switched the position of the source and the load, and this circuit will be like this. Suppose we have a capacitor, source here, then we have one source, inductor, then we have one source, then we have another source, then it is connected to a capacitor, and then it is connected to the load. Suppose now this is my output V naught and this is my input Vs. So this circuit is this circuit, right? We just made 180 degree phase shift, right?
Yes, sir.
So what we can do here for this switch now, we can choose, suppose this is my source voltage Vs, this is my inductor. Then instead of this switch, suppose this is my switch 1, this is my switch 2. So what we are doing, we are considering a transistor here, which is my T1. And then instead of this switch S2, we are considering a diode here. And then it is connected to a capacitor. And then it is connected to a load, plus minus V naught. This is my C, this is my L, this is D, and this is my R, since we are considering a DC load. So what will happen here is that this circuit will operate like a boost converter. Why? Because we switch the position between the source and the load. So let us check whether what we are saying, it is actually operating like this or not. Is there any question or any confusion why we choose the choose to switch the position between the source and the load?
No, sir.
So now, similar to the previous case, suppose we are considering the output voltage, like this is my VBE. So this VBE is on for a certain period, and then it is off for a certain period. Then again, it is on for a certain period. And then again, this is off for a certain period. So this is the voltage waveform for VBE. So whenever you are putting pulses here, this switch will turn on or off.
Turned on.
Turned on or off.
On.
On. Okay. So suppose this switch is on for D into Ts time, and this switch is off for 1 minus D multiplied by Ts time. And you know how this equation comes from, right? So like the buck converter will have the two mode operation. Like in mode 1, we considered that your switch T1 is on for D multiplied by Ts time. So when the DS is on, what will happen? So when this T1 is on, then what will happen? So the circuit will look like this. So you have an inductor, and then this T1, it will look like a short circuit switch, right? Because it will turn on, right?
Yes, sir.
And there will be a diode here in this direction, and then you will have a capacitor, and then it should be connected to a load, that is your plus minus V naught. So if this diode is connected here, so the terminal, this point, suppose this is my A point and this is my K point. So A point voltage would be 0, right?
Yes, sir.
A point voltage would be, because this is short circuit and this thing is connected there. So this is short circuit. So the potential appear here, it would be 0, right? And K terminal, it is connected to plus V naught voltage. So should this diode operate or it will be in reverse biased?
The reverse bias.
Reversed.
Reverse bias. So practically, this diode will not operate. So what will happen? Suppose we are considering this voltage to be my VL voltage and current is going in this direction, that should be my IL. This current here, it should be my I naught, and this capacitor current, this should be my IC. So what will happen here now? Then the input voltage, it will appear across the inductor, right? So your inductor voltage VL, it would be equals to VS, right? Right, because this is short circuit. If you take the Kirchhoff's voltage law, you will find that all the source voltage, it will appear across the inductor, right?
Yes, sir.
So that should be equals to my L multiplied by, since the interpositive voltage is appearing across the inductor, the current would be changing. So we are considering this current to be IL1, and it is happening for d multiplied by Ts time. So that should be my d multiplied by Ts. So from here, we can consider that my del IL1, it would be equals to Vs over L multiplied by what? D multiplied by Ts, right?
Yes, sir.
So my Vs is constant, L is constant. So the current will ramp at a constant rate, right?
Yes, sir.
Is there any question regarding this? Suppose this is my VL. So for this period of time, your VL, it should be equals to Vs. And the current, if you draw the current IL, so likewise, it will have a ramp current like this, ramp current like this, when the switch will be on. So then for mode 2, what will happen? So for mode 2, this thing will turn off. So whenever this thing is turned off, then the circuit will look like this. Okay, one more thing. During mode 1, if you take the Kirchhoff's current law at node here, what you will find? IC plus I naught, it should be equals to 0, right? So your IC current is nothing but your I naught current, right? For this circuit. Right?
Yes, sir.
Okay. Now, for mode 2, this inductor current is going like this. This is my VL. So this current will turn this diode on. And if this diode is turned on, then what will happen? Instead of this diode, what we can do? We can consider a simple switch that is short circuited. So this should be my T1 and this is my D1. Okay, so I made one mistake here. So here it should be an inductor. So the circuit should look like this, right? So now what would be the voltage across the inductor?
PS minus V naught.
So VL is nothing but this terminal is connected to VS. This terminal is connected to V naught. So it should be VS minus V naught. That should be equals to L multiplied by, since actually this term, it should be negative. Why is that? I will be explaining that. So it should be del IL2 over 1 minus D multiplied by TS, right? So that gives you del IL2, it should be equals to VS minus V naught over L multiplied by 1 minus D multiplied by TS. Suppose this is your equation number 2. So this is my equation here. So if we do the voltage current, voltage second balance, so using volt second balance, we know what we know. The integration over a switching time V of lambda d lambda, that should be equals to 0, right? So what was the voltage across the inductor during this time? This is your VS, right? And this is happening for D multiplied by TS time, right? And what
Yes.
was the voltage across the inductor during 1 minus D multiplied by TS time? It was VS minus V naught. And this was happening for 1 minus D multiplied by TS time. So it should be 1 minus D multiplied by TS time. That should be equals to 0. So we can write VS D multiplied by TS plus VS minus V naught multiplied by TS minus VS minus V naught into DTS. That should give you 0. So if you simplify that one, what you get? VS D into TS plus VS TS minus V naught TS minus VS into DTS minus plus V naught into DTS. That gives you 0. So this term and this term will cancel out. So we can write Vs multiplied by Ts. It should be equals to V naught Ts and minus V naught into dTs, right? Or we can say Vs Ts, that should be equals to V naught. If you take common, then 1 minus d multiplied by Ts. So if you cancel this out, so your V naught is nothing but 1 over 1 minus d multiplied by Vs. So if you consider your V, it would be greater than or equal to 0, then G less than 1. So what will happen when D is 0? So when D is 0, then what will happen? Your V naught will be equals to Vs, right? But if your D is, we are considering D in this region, then what will happen? Greater than 0, but if we are considering D is greater than 0 but less than 1, then what will happen?
The output is greater than V source.
As the D value will increase, but it is less than 1. So what is happening? If your D value is getting higher, so what will happen? Sorry, if you put D value lower, suppose like we are considering it D equals to 0.5, then what will happen?
V output will be
2 Vs.
twice 2 Vs.
So your V output would be twice of V input, right? So if you operate in this region, then what will happen? Your V output will be greater than your V input, right? So that's why this is known as boost operation. And the converter that we discussed here, it will be a boost converter. Now, one more thing. So if your V naught is greater than Vs, so should this value positive or negative?
Negative.
Negative. So during this time, when the switch is off, the voltage across the inductor, it would be a negative value. So this value would actually equal to Vs minus V naught. This will be the negative value, and similar way it will repeat like this. And you will simply say the area here is positive. This area should be negative in order to, if we integrate from here to here, this will add up and becomes 0. That is what the volt second balance says, right? Similar to the inductor current, since this value is negative, so the current will have a negative slope here. So instead of during this time, it will be charging down up to this point, and then again it will charge up when there will be a positive voltage here, and then whenever the voltage gets negative, it will charge down to 0 as well. So the current waveform will be similar to what we had for the buck converter, but the voltage across the inductor will be different because we have switched the position between the source and the load. Any questions so far?
No, sir.
So uh, let me finish it here for today. If you have any question, you can ask me. Otherwise, I will provide all the videos and the lecture that we covered last class and today's class. You just go through it. And if you have any question, you can ask me in the next class. And then we'll start from here. Okay. Is there any question as of now?
Sir, sir,
Yes.
in the buck converter last in last class, you nullified the current that was going through a capacitor, and you told me that you will answer it later on. But here in boost converter, you considered IC, I mean current through capacitor.
Yeah, it will be, we have just only considered the inductor current and the inductor voltage and the inductor current, right? So we haven't drawn all the waveform for the boost converter. So if you understand these things as of now, we'll try to describe the waveform for all other things, right? So in mode 2, what will happen? This inductor current will go here, and then it will be divided in these two branches. So that should be my IC, and that should be my I naught. So what will happen here? Your IL would be equals to IC plus I naught, right? Which was in the previous case, your IC is actually negative of I naught, but in this case, your IC will be the difference between, so we can write your IC will be difference between your IL minus I naught, right? So you just go through all the condition that we derived for boost converter, and using that equation, we'll try to draw all the waveform for the boost converter, and we will discuss what is happening through the capacitor and the inductor in terms of voltage and current and the power as well. Okay.
Yes, sir. Thank you, sir.
Any more question?
Yes, sir.
No question? No question means two things. Either you have understood everything or you have understood nothing.